Yeah, dear all, welcome to the last lecture in our electronics course here. Last lecture, we talked about analog to digital converters and digital to analog converters. I'd like to ask if there are any questions. Please speak up or write them in the chat. So to recap that whole subject, here I looked for a comparison of the performance of an ADC, and there's a nice publication you can see here that is like searched for all different publications on ADC performance. And so what you see here is the effective number of bits. So that's like the resolution an analog to digital converter has. So if you convert the noise that you see in your signals to an effective number of bits, so this is like the significant digits in the data that you get. Everything else is noise. So it can be that you buy a 24-bit ADC, and if you sample here at 10 kilohertz, you get at most something like 18, 19 effective bits of data, and the rest jitters around and is noise. Yeah, then you see how this effective number of bits, so the noise in your digital signal, evolves as a function of sampling rate. And we see, okay, of course, if we sample faster, then we get more noise. And in principle, if you then take the many samples that you get here, for example, at 1 megahertz, and you could in principle average then a few of those samples, and then you can walk on those lines here towards higher resolution and smaller sampling rate. And that's actually exactly what the filter here in the delta sigma ADC does. So what we get here basically is a very fast signal with 1-bit resolution, and then this filter kind of averages over a few samples and then gives us a higher resolution signal with a smaller sampling rate. By the way, this is also one advantage of this kind of filter, that the actual analog circuit here is sampling at a very high frequency, typically tens or even hundreds of megahertz. And for that reason, and then of course we cut with a very efficient digital filter all the high frequencies. And for that reason, those ADCs are pretty much immune to aliasing, because the aliasing signals would end up somewhere here in these high frequencies, which are cut anyway by the filter in the digital logic. Okay, now coming back to this comparison, and then you see as a function of time, so red is 1990, and you see here in the 30 years since then, for example, at the 10 megahertz sampling rate, we gained basically 5 effective bits, which is quite a lot. So this you get now much better ADCs at that particular sampling rate than 30 years ago. And it's of course, this will of course go on. You can parameterize basically the performance of all the ADCs with the slope, or with the where this slope is. And what's drawn here as a comparison is the noise in a 2 kilo ohm resistor. So you see that the noise that we get nowadays basically is the same that you would get in a 2 kilo ohm resistor with a signal that is full scale of 1 volt. So you can get a bit better than that, if you use a full scale that is larger than 1 volt, plus minus 10 volts is the largest you can typically use in an electronic system, but it's kind of old school. Nowadays, we want to be energy efficient, and then it's more like 5 volts amplitude is the maximum you can have. So you can do a little better than this by using a larger full scale, but 1 volt is also typical. And then you see, okay, I mean, the noise that we get is limited or is the same than you would get by a 2 kilo ohm resistor, which means that the largest resistor that you can have in the input circuit before your ADC, if you don't want to degrade your noise, is 2 kilo ohms. And then, okay, yeah, if we improve the performance a little bit, then it would be equivalent to a 50 ohm resistor. Let's say in another 20 years, we will see that. And then this means that the noise of the amplifiers that come before your ADC has to be correspondingly small. Okay, and you see, okay, the performance basically follows those lines. We remember one lecture ago, I told about resistor noise and that it scales with bandwidth, like the square root of the bandwidth. So let's quickly verify this. Let's take this point here and this point here. Between here and here, we lose 10 bits in resolution. This is a factor 2 to the 10, so 1024, or 3 orders of magnitude between here and here in resolution. So if it goes with the square root, it must be 6 orders of magnitude in sampling rate, and that's exactly the case. So it's a 1, 2, 3, 4, 5, 6. So we got here. So those lines here are basically simply the square root law that we always find in these noise calculations, and the same square root law that you find if you average a signal. Yeah, so if you take the 10 million points you get per second here, and you average 100 points, you reduce your sampling rate to 100 kilohertz. So here, and then you increase the resolution correspondingly by a factor 10. Okay, so this gives you an overview what kind of performance we can expect from a state-of-the-art analog to digital converter, and basically that dictates how high resolution measurements we can do in our field, because nowadays basically every signal we encounter somewhere in an electronic system goes through an analog to digital converter before we look at it. Okay, so that concludes the section about ADCs and DACs. Now, the last chapter in this lecture is closed loop control. So what is closed loop control? It's in concept very similar to an op-amp circuit where you have well, an amplifier, and then you measure some kind of feedback in order to make everything better. So closed loop control, you have an input here to the controller. And this kind of measures something in your process that you want to control. And then the controller compares this input to a set point. And the set point typically is a voltage that you can define on the outside, or you can set it somewhere inside your device. And then the first thing the controller does is it builds the difference between the two. And the difference between the input and the set point is called the error signal. It's abbreviated epsilon. And then the controller changes its output, with which it somehow controls the process, such that the error signal becomes as small as possible. It always tries to get the error signal to 0. Okay, an example for closed loop control is this device where you have a heating plate and then a temperature sensor, and you can put your beaker with, I don't know, water in a chemical lab onto the heating plate, and then you tell the device, here the set point, I want this to be exactly 40 degrees. And then the device measures the temperature inside your water and regulates the heater such that it's always equal to the temperature that you've set here. And of course, this is a useful concept for many parameters, especially in physics experiments. If we go a bit more to laboratory equipment, PID controller, or I mean, this kind of control is done with a PID controller, and PID stands for proportional integral differential. And in a minute, we will see what that is. And here you see a nice example of such a device. It's a small electronic box with an input. It's called measure here. Then you have an input for the set point, and you can choose if you want this external set point voltage, or if you want to specify the set point internally using the digital interface here. And then, of course, you have an output with which you can control some parameter in your system. And then on the back side, you also have an output for the error signal. This is important to monitor the performance of your regulator, and you get another copy of the internal set point if you want to record that, for example. And then this has a digital interface to control this remotely. So what's inside? I mean, the box looks very digital, but inside is an analog PID controller, pretty much exactly built like this one here. Of course, with more components around it to do a few more service things, but the main components are exactly what you see here. And the way this is controlled is done in a digital way, and I will explain that in a minute. So what you see here is the input and the set point, and those go to a difference amplifier. So this is one of the components we have talked about in the lecture about op-amp circuits. So it's the classical difference amplifier. And this, of course, then is our error signal, and this goes to the error signal output, where you can measure it and control your monitor the performance of your controller. And then with the error signal, three things happen. The first branch is simply a buffer, so we get a 1 times copy of this to the output. The second branch is the integrator. So we have also seen this as an op-amp circuit. If you have the capacitor here in the feedback system, this integrates the input signal. And then we have the opposite. This circuit builds the differential of the input signal. So this differentiates our error signal. And then these outputs here are added in a free branch adder with the same resistors in each branch, and then one additional resistor in the feedback loop with which you can set an overall gain. And now the three parameters with which a PID controller is set up is the overall gain, the integration time constant given by Ri and Ci, and the differentiation time constant given by Rd and Cd. And then it's simply it's easy to calculate the output signal. So we again define our error signal as the difference between the input and the set point. And then we can calculate the output. It's the overall gain, P, for proportional gain, times, well, 1 copy of the error signal that we got here, and then times the integration of the error signal, and times the differentiation of the error signal, So we add up the copy, the integral part, and the differential part. And well, the integral part and the differential part are characterized by time constants that you see here, which are necessary to make this dimensionless. And we will have a look here what they actually mean. So if we have a look at this integrator, so it's also called the I part of the PID controller. Well, it integrates the signal, of course. And so this means that a constant signal leads to a linearly growing output. So if we integrate a constant, we get a linearly growing output. And this voltage, which is just the output of the integrator, it takes the characteristic time, Ti, to grow to a value equal to the direct copy. So in the sum, if we have a finite constant error signal, then it takes 1 time Ti such that this term is equally important than this term. Yeah, so the integration part has a built-in time constant that makes it like a delayed response. And then on the other hand, the D part, the differentiation part, so in order to get something out of that, we have to have a changing error signal. So let's say we have a linearly changing error signal. And then we can calculate if we have a slope on this error signal, how large is the voltage that we get out of the differentiator. And this we can characterize by the time that corresponds on this slope to the voltage that we get. And so the larger this time is, the larger the contribution of the differential part. And so the characteristic time gives us the voltage simply by saying, okay, the total change of this linear slope in the time that we set, this gives us the voltage that we get. But this does not mean, I mean, if this is 10 hours, yeah, and we have a signal that changes with a millivolt per minute or so, then it doesn't mean that we have to wait 10 hours. We get this output already directly after the first second, as soon as this has settled. It just says that the voltage we get is equal to our slope times 10 hours. So the larger this time is, the larger is the voltage, the larger is the strength of the D part. Okay, and so let's put all this together. And in order to show results, we also need a process to control. And in this case, I've chosen a really simple process. So the output of our PID controller goes simply through an RC filter, a small low-pass filter, and then back to the input. Now, an RC filter or a low-pass filter is not unrealistic at this point. For example, if we go to the example of the temperature controller, if you set, or if you start heating here, then it will take some time until the water changes its temperature. And that's exactly the behavior of a low-pass filter. So one could say that this is a simple, very simple model for a process that we want to control. Okay, and now what we do is we start with a set point of 0, and then everything is in equilibrium when everything is 0. And then we do a step in this set point and see how the PID controller reacts to that. And this is equivalent to having the temperature controller. Everything is at room temperature, everything is in equilibrium. And then we tell it, now we want 40 degrees, and then it has to heat up in the right way such that we approach 40 degrees and stay stable at 40 degrees. Okay, and so let's first deactivate the integral and differential part and only have a look at the proportional part. So it's called P control for proportional. And so we only get the output in this example here of the P part. And then, okay, what you see is everything is in equilibrium here at 0. And then at some time, we change the set point to 3 volts. And it stays at that voltage all the time. Now, if we have a really, really low gain, so a small proportional amplification, then what the regulator does is it goes up a little bit, but not really a lot. Now, if we increase this gain, it comes closer to the set point. So it tries to minimize the distance to the set point, but not really very close. Yeah, and so what we see here is the output voltage, the input voltage, yeah, which is equal to the output voltage after the low pass filter, and the corresponding error signal. Yeah, and so the larger the gain is, the smaller can be the difference between the set point and the input voltage, because this difference is then amplified and gives the necessary output voltage. Now, and you see at a gain of 2, we have an error signal of 1 volt, and we generate 2 volts of output. Yeah, so you see we come like 2/3 of the way towards the set point. And of course, I mean, this is not really satisfactory yet. If we tell an temperature controller that we want to go to 300 degrees and it only goes to 200 degrees, this is kind of not the point of having a good controller. So the solution would be to increase the gain. And here I have drawn one example where the proportional gain is set to 7. And then you see already, okay, we come closer to the set point. So the error signal becomes smaller again. But it also starts to oscillate. And this is typical behavior. If you increase the gain on a servo controller, then at a certain gain, you will start oscillating. And this might still be acceptable to have a few oscillations and then stable operation. But in principle, you would like to avoid that and go smoothly to the set point. And I mean, this is very, very related to the lecture by Wolfram about amplifier stability. Here, it's basically the same. It's the stability of our PID controller, which is at risk if we increase the gain too much. Okay, so what's the solution in order to close this gap and really have the out or input voltage equal to the set point? But the solution is to use the integral part, as you can see here. Now we activated the proportional gain and the integral part. So this is now called PI control. And in many circumstances, that's already sufficient to do proper control. So you find PID controller in the lab everywhere, but many of them are also just PI controllers. Okay, so what does the integral part now change? Let's have a look at the orange curve here. And here you see that it settles to the same 2/3 that the proportional would give us. Yeah. So if you look at the blue curve here, oh, sorry, the colors are not the same. If you look at the blue curve here, it looks pretty much exactly the same as the beginning of the orange curve. And then we said, okay, we can choose with the time constant of the integral part how long it takes before the integral part becomes more important than the proportional part. And in this example, the orange curve, this integral part was, I mean, the time constant was chosen very long. And so you see, okay, it almost settles to the proportional part situation. And then slowly, the integral part kicks in. Yeah. So what the integral part does is it integrates all the error voltage that we had between here and here. And then at some point it says, okay, I mean, this sums up to a sizable contribution. And then it continues to integrate, and you see the error voltage becomes smaller and smaller. And so the part that is added to the proportional situation where we would stay at this level here also becomes with time smaller and smaller, and we exponentially approach the set point. Okay, but of course, this is still not ideal behavior since it takes a long time here to approach this set point. So this integration time is too large. Now the blue curve here, I've tuned the integration time to look nice. So what we get is a rather quick approach, and then it basically immediately settles and stays at the set point. So this is close to optimal performance of such a regulator. You know that we have in our example, we have a low-pass filter here, and this low-pass filter cannot change its output voltage arbitrarily fast. And for that reason, we also cannot change approach the set point arbitrarily fast. Yeah, and under the given constraints, so under the given time constant of our process, this is about as good as it gets. Yeah, you can do a little bit better, as the the green curve shows you here. So we go steeper towards the new set point, but then we have to live with those oscillations. And sometimes it's an issue that you want your controller to reach a given set point as quickly as possible. And then you might be willing to accept the oscillations, but typically you wouldn't want that. And so you see that we have already seen two ways to make the system oscillate. One is to have a large P gain, and the second way is to have a small TI time constant. And yeah, so typically what you do is if you set up an PID controller, you well, crank up the gain and reduce this time constant until it oscillates, and then you put it a little bit back. Okay, now what is the D part good for? So the D part generates a contribution to the output that is proportional to the change of the error signal. And so here we have to have a look. You see we have the set point, and this is actually not an instantaneous change. I included a small slope here, and you see that the set point starts to change. And this in principle immediately, so the difference between the curves here, the output curves, and the set point, this is the error signal. So you see the error signal grows very quickly here in the first moments of this of the change. And in the D part will then generate a large voltage proportional to that change. And this gives the whole system a kick in the right direction right in the beginning. And the way we see this here is, of course, the low-pass filter in our process swallows this kick, but we see that we start approaching the new set point a bit faster if we have a PID controller than with a simple PI controller. And that's the goal of the D part, is to have, if you have a sudden change, to react more quickly than the P and the I part can do. It's typically a subtle change. So what you would do if you set up a PID controller is to first get it into stable PI control, and then see if you can optimize the situation by activating the differential part. And in many circumstances, it's not necessary. Okay. Yeah, I'd like also to mention stability. So if we have a look again here at this change in set point, and the blue curve is close to optimal performance that you can get in this situation. But what happens if we choose our time constants wrong? Also with the D part, you can get the amplifier to oscillate. And then we distinguish between like 3 escalation steps of oscillation. So barely stable, you can have a damped oscillation. So it starts to oscillate, but as you see in the green signal here, the oscillation amplitude then decreases. And this would get completely stable after some time. And this might be acceptable. It can also happen that if you increase the gains more, that you get to a barely stable situation with a bound oscillation. So here you see that it was stable in the beginning, then we changed something, and then we went into this oscillating state, and the oscillation amplitude decreases a bit, as you can see here, between this and this and this maybe, but then stays constant. Yeah, and it will oscillate forever if you don't change anything in your system. And this is typically unacceptable because, I mean, it will simply mess up all the signals in your system. And then, but okay, this is still in the dynamic range of our amplifiers. And then really unstable, unbound oscillation is the gray signal you see in the background, where the amplifier really goes to its most positive voltage and then drops to its most negative voltage and rises to its most positive voltage again. This is then completely unstable. All the amplifiers are at the edge of their supply voltages, and this is to be avoided. It's not a stable situation. For example, if this would be a temperature, also the temperature that you get out would have nothing to do with the set point. Whereas the bound oscillation here, you see it kind of oscillates around the set point value. And if we would change the set point, it would also oscillate around a different value. But you also see that the average between this and this on the orange curve is not equal to the set point. Whereas in the damped oscillation, the average stays at the set point. So that might still be acceptable, depending on your application. Okay, now this concludes the part about PID control. Are there any questions? Okay, I don't see any. There's one thing I'd like to mention here again. I've mentioned that this reaction time that we see here is roughly the fastest you can go given in a certain system. So, I mean, the time constant of our process does not allow us to go significantly faster than the blue curve here. But sometimes it's not desirable to go as fast as possible. I've seen some systems where the PID controller was also used as a kind of low-pass filter. And so this you can achieve with a large TI time. So if I write here that TI is too large, that's true if your goal is to be as quick as possible. But sometimes your goal could be to suppress noise because maybe your input signal is a bit noisy. And then a large TI time can help. And in addition to being a PID controller, it also acts as an additional low-pass filter. Okay, so that's the part about PID control. And that basically concludes the content of the lecture. What Wolfram and I would now like to do is give you a bit of examples where actually electronic systems occur in our daily work. And I will start with the experiment that I'm working on currently. So this is the neutron EDM experiment at PSI. So all the work we do is here at PSI, quarter of an hour away from Baden or Bruck, at the nice Aare River, where we have a large accelerator. Well, large for PSI standards, not large in general, not nowhere near as large as the accelerator, for example, at CERN. Okay, and what we do here is we search for particle properties. It's a high precision particle physics experiment. And the fundamental reason why we are interested in that is the baryon asymmetry. Baryon asymmetry measures how much matter and antimatter, so NB and NB dash is like the number of matter and antimatter particles in the universe. And if this, well, what we observe is a lot of matter in the universe. So this value has a finite number. It would be 0 if we have the same amount of matter and antimatter in the universe. Yeah. And we see that our universe exists and consists of matter. There are very sensitive tests that can tell that it's all matter, not somewhere a galaxy made of antimatter. And so we can see that this value, which measures the amount of matter in our universe, must have a certain number. Now, if you paint the same picture according to the standard model, and the standard model of particle physics, I mean, it predicts so incredibly accurately how all the particles behave in the large accelerator experiments. So it's a hugely successful model of our world. But if you predict the same picture according to the standard model, it looks like that. There is absolutely no matter. The standard model does not include an efficient process to create matter after the Big Bang. Or, I mean, to create, it would create matter and antimatter in the same way, very symmetrically. And then the two would annihilate, and there would be no matter left. And so if you quantify that, the Baryon asymmetry predicted by the standard model is 8 orders of magnitude smaller than the one that we observe. And I mean, imagine in a universe with 8 orders of magnitude less matter, it's basically nothing to see there. Okay, now there is a connection between it's clear that we have to find a theory that can predict why actually we have matter in the universe. And of course, many theorists are working on that. And here's a selection of such theories. And then so of course the question how to test such theories. And some of the theories, they predict particles. And of course, you could look for them directly in large accelerator experiments like the one Wolfram will talk about in a moment. But we take a different approach. We say, okay, those theories, they also predict properties of particles that we already know. For example, the electric dipole moment of the neutron. Their predictions are very different than the predictions in the standard model. So if we can find such electric dipole moment of the neutron, it's a property that has been looked for many years, then we could decide, or at least get a hint, which of those theories which can predict why we have matter in the universe would actually be, could be, I mean, the theory that actually describes our universe. And well, here you see the experimental sensitivity to this parameter, and the plot is a little bit outdated. We just published a better limit. But until now, this quantity has not been found. And so it's of high interest to search for this quantity. And that's what we do at PSI. And we use a very special kind of neutrons to do that. We use ultra-cold neutrons. So we use the accelerator at PSI to make neutrons. And then we cool them down to really, really small velocities. So it's kind of the opposite approach of CERN, where you deal with very high energies. So our kinetic energies of the neutron is like 300 nano electron volts. And the velocity of the neutrons is good pedestrian speed, so smaller than 7 meters per second. And actually, they're so slow that they can't escape our source to the top just because of gravity. They just fall down again. Another interesting property is that we can guide those neutrons into our experiment from the source to the experiment because they totally reflect on neutron guides. And that's, I mean, they're so slow that they cannot penetrate the material. So this is an efficient way to generate neutrons and to fill them into an experiment. And then we can actually close a shutter at the experiment and observe the neutrons for hundreds of seconds. And what we measure is the Larmor precession frequency of the neutrons. And for the purpose of this introduction, all you need to know is that the Larmor precession frequency depends on the magnetic field because the neutron has a known magnetic moment. And if there is an electric field, then it also depends on the electric dipole moment. So there's a magnetic dipole moment, which leads to precessing neutrons. And if there is an electric dipole moment, then also the electric field would contribute to the frequency with which the neutrons precess around the magnetic field. Now, if you change the direction of the electric field, then the contribution from the electric dipole moment should be reversed. So we should see a different precession frequency between this situation and this situation where we have reversed the electric field. Now, the only problem in doing such an experiment is that the magnetic field between these two has to be exactly the same. And so in order to get a hint why we have matter in the universe, we want to measure the difference of these two precession frequencies. And in order to do that, we need to make a really, really, really stable magnetic field. Best magnetic field stability in the world. Okay, and then the experiment works like that we fill the neutrons into our experiment with a radio frequency pulse. We flip the spins. Then in addition to the neutrons, we also have mercury atoms inside this volume here. And just to mention a few things that are important here, we monitor, this is a mercury laser beam which goes through our experiment, and we monitor the power of this beam with a photodiode. We want this power to be as stable as possible. So we have a monitoring photodiode here that sees parts of the beam with this beam splitter. And so this, for example, is a PID controller that tells the laser if this power here deviates from the value that we want, and then it changes the power in a feedback loop, such that we have a really nice stable power going into the experiment. Now, inside the experiment, the mercury atoms absorb part of this light, and we see very characteristic free precession signals from the mercury that allow us to measure the magnetic field, which is very important for this experiment. So to read out the photodiode, we need a transimpedance amplifier, so basically an amplifier that converts a current to a voltage in order to digitize this signal as good as we can. And so those are all components we have seen in our lecture. Yeah, we are just setting up a new experiment, which has one more trick to be better than the last one. We have two such volumes where the neutrons are. The electrode that makes the electric field, the high voltage electrode, is in the center. And then on both top and bottom, we have ground electrodes. And this means that we get the situation where the electric field is parallel to the magnetic field in the upper chamber, and the situation where the electric field is anti-parallel to the magnetic field in the lower chamber. The experiment is much larger than our old one, and because we can measure both things at the same time, gives us a lot of advantages to suppress systematic errors. So what can I show you of this new experiment? You see here a large magnetic shield. It's 5 by 5 by 5 meters, which shields all disturbances from magnetic disturbances from the outside by something like 5 orders of magnitude. But that's not enough. And so we need one more system to suppress magnetic field fluctuations. And I will get into the details after the break. So see you at 1:45. Yeah, okay, let's continue. So I was talking about the magnetic field that has to be very, very stable in order to do this experiment. So this shield here consists of mu metal. It's a metal that has a very high magnetic conductivity, so high permeability, and so as I said right in the beginning of the lecture, the reason why we have electronics and not magnetronics is that we have materials with which we can direct electric signals because we have conductors and insulators. And the difference in electric conductivity between the two can be, I don't know, 18 orders of magnitude. So it's easy to conduct an electrical signal to a certain location. With magnetics, it's different. The best magnetic conductors we have are maybe 6 orders of magnitude or 5 orders of magnitude better than just air, which is like the worst magnetic conductor. And for that reason, in order to shield a volume from magnetic signals, you need this huge magnetic shield, which consists of layers and layers of shielding material. And the magnetic field from the outside likes actually to go better through the shielding material, and thus it goes around the experiment. So inside here you see the gray areas. This is the shielding material in many layers, and the magnetic field goes around our experiment, which will be installed inside. But inside, of course, we do need a magnetic field, and that's generated by a small coil, which then generates exactly the magnetic field we want. So the strategy is to suppress everything from the outside. At PSI, we have to live with superconducting magnets that are next door. So we want to suppress all of that, and then inside generate a magnetic field that is as perfect as possible. And so in order to suppress those disturbances from the outside, of course, the shield itself has a shielding factor of 100,000, but that's not enough. And so one more layer of protection then is a structure around this shield with many, many coils, like 300 coil loops, and then magnetic field sensors that measure the magnetic field, and then a complicated PID control that takes the 30 sensor values and controls 24 current sources, which then drive a combination of these 300 coils, such that the magnetic field inside does change as little as possible if a superconducting magnet next door switches on or off. And here is a bit a few components of this system I can show you. The coils are currently being wound. So you see this is a panoramic view of the top of our magnetic shield. So this is the 5 by 5 by 5 meter magnetic shield. And here we are on a scaffolding at the top level of this shield. And then you see we've built a wooden house around the shield, which has, this is like 10 meters long and 9 meters high. And now here we are on the top level of this wooden house, where you see the many cable ties, which are now being populated with coil wires that you see running around here. And then some coils, they have complicated shapes, and it was actually a PhD thesis from ETH, a brilliant student who calculated all the 300 coil paths that produce exactly the magnetic field, which cancels the disturbing fields that we have in our area. Yeah, then we have to measure the magnetic field. We will use flux gate sensors that look like this. So this is like a 2.5 centimeter diameter tube. The PID controller now, it's a bit more complicated than the one that I showed you because it has 30 input parameters and 24 output parameters. So it has like a vector of input parameters, a vector of output parameters, and a complicated matrix relating the two. And so for that reason, it's called matrix feedback. And this is implemented digitally with, of course, then analog to digital converters for all the sensors and digital to analog converters for all the power supplies. The power supplies themselves are purely analog, as you can see here. So there's a big transformer which supplies the power. Then you have a huge heatsink here with a radiator. On top of those are large power transistors, and they are then controlled by an operational amplifier. And the nice thing about those large amplifiers is, in principle, they act like one big operational amplifier, which can deliver, in this case, 15 amperes and 50 volts, so quite some power. But the whole function of this device is controlled by a small board where you can select which components are in the feedback path and which components are on the inputs of the operational amplifier. So exactly the same thing we've done in our lecture. Also exactly the same problems. This amplifier was unstable, and we had to add a capacitor in the feedback loop to make it stably drive the huge impedance of these coils around our experiment. So this to give you an example that the things that we had in the lecture are actually pretty much out of the daily life in our experiment. There's one more nice project I'd like to show you. In order to make the current in this coil here that generates the magnetic field inside our experiment. So now imagine we have suppressed all the disturbances of the magnetic field. We have temperature stabilized everything perfectly. And then we have this coil right next to the heart of the experiment that produces the magnetic field we want. This means that we need a current in this coil that is as stable and nicely behaved as possible. And this here is the power supply for this current. In order to make a stable current, you need two things. You need a voltage reference and a reference resistor. Yeah, and then using Ohm's law, you need an amplifier that keeps, well, drives the right signal to your coil such that the current that flows through the coil and then through the reference resistor, so those are in series, exactly to the voltage value that you want. This is how you make a really, really stable current. And I've shown you with the ADC performance chart that there is like a limit how well you can do that. And of course, if you want to be better than that limit, there's one way, and this is duplicating your components. Yeah, and then you kind of average over many components. And this is what we do here. So we have not only one voltage reference, but 8 voltage references, which then gives us square root of 8 better performance. Everything in this board here is temperature controlled to better than a millikelvin. So you see this huge aluminum plate, like 20 kilograms of aluminum, is like the thermal mass, and then there are Peltier elements that control the temperature of those smaller aluminum plates on which then the boards are mounted. And each component in the boards is contained in a small house that there can be no air going over it, and that it's again isolated also from electromagnetic interference. So this board here is just to make a stable reference voltage. This board here detects the current, and you see it's also several reference resistors. And then this board is the main amplifier. And one special thing about this whole setup is that we can choose, or we can continuously change the current. And so we need DACs to divide down the reference voltage to the value that we want. Those are actually the DACs that I showed you in the lecture, and we have 10 of them. Also, again, to average over multiple components and reduce noise and improve stability. And then the amplifiers themselves are the highest grade, and again, built with multiple components and in a very symmetrical way to suppress disturbances. And then finally, the output is also something special. It's looks like a BNC connector, but it's a triaxial BNC connector. So this means in the center, you have a wire that carries the current to our coil. Then as the next layer around it, this would be the shield of a normal BNC cable. You have well, a shielding mesh that collects the current and directs it back to the amplifier. And then around those, you have one more layer that's just a shield to minimize disturbances. And all this together now, you see this is a CAD model. So this system is being built up, but by testing individual components, we could estimate that the stability of this current source is 2 parts per billion. So in the lecture, we've often talked about parts per million stability or accuracy. And so parts per billion is still 1,000 times better. Yeah, 2 parts per billion stability is brilliant performance. But it also tells you, I mean, have a look in the RC lecture, how many time constants you have to wait until something settles to a part per billion. The materials have to be chosen in a special way. If something has a too high conductance, for example, the material of the printed circuit boards, then you get small currents through the printed circuit board where actually there's no trace, which at the part per billion level could affect the current that you're generating. Okay, and yeah, well, this is a nice project. And soon this will be handed over from the engineering department to the physicists, and then we have to test it. And this is just one example of interesting projects we have to offer. So if you want to have a look at research at Paul Scherrer Institute, you are very welcome in my group as well as in Wolfram's group. We have semester projects, master projects, bachelor projects, and PhD thesis pretty much all the time. So if you're interested, please drop us a line and we can get in contact. Yeah, I would have loved to show you, organize a lab tour to PSI, but due to Corona, that's unfortunately not possible this year. Okay, but if you're interested, please let us know and maybe we can organize something. Yeah, this brings me to the end of my part of the lecture. Thank you very much for sticking around and for your attention. As you know, the lecture continues next year with the digital part by Yves Ackermann, and I highly recommend that you join that lecture. I would like to say thanks again for the lecture ratings. They were very good in general, and thank you for participating. Yeah, with that, I would like to hand over to Wolfram, who will take the remaining time to tell you interesting things about his experiment at CERN. So thank you very much.
Okay, Georg, you need to enable sharing.
Ah, okay.
Okay.
Okay, should work.
Let's see. Yep. Okay, do you see this?
Yes.
Okay. Okay, so as Georg said, I will now present a little bit about what my group does. So we're both in the laboratory for particle physics, but my group is the high energy physics group. So we're at the other end of the energy scale. So Georg just said that their neutrons have an energy of 300 nano electron volts, and we work with the beams at the LHC, where the protons have an energy of 7 tera electron volts. So that's 19 orders of magnitude higher energy. So we're kind of the opposite end of those scales here. What we do with these collisions, the point of colliding particles at such high energies is that we can not only look at what is inside these particles by shooting them at each other, but we can also create new particles that were not constituents of the colliding protons, but that are in fact heavier than the two particles that we shoot at each other. So this is, of course, you've seen E equals mc squared. So if you pump enough energy into such a process, you can create particles that are much heavier than the proton. So the mass of these particles can go in principle up to the beam energy of the LHC. And the purpose of this is to study the fundamental forces and the constituents of the matter around us. And this is all summarized in the so-called standard model that that Georg has already mentioned. And so the aim of these experiments is to probe the standard model and similar, but in a different way to look for extensions or modifications to it that might explain, for instance, the matter-antimatter symmetry that Georg has already mentioned. Okay, so colliding particles is not enough. You also need to detect what happens. So you need to surround the collision point by a hermetic detector, and then record all the particles that fly away from these collisions. So this photograph shows an aerial view of the CERN area. So CERN is here roughly. This is the airport of Geneva, the Lake Geneva, and this is the LHC tunnel, which is about 100 meters underground. And one of these places here is our experiment. And there we need to have a detector that surrounds the point where these particles collide, the protons collide, and then we must detect all the particles that fly away from this collision. Many of them, especially the interesting ones, decay immediately afterwards, but they decay into other particles which we then can detect. And if we detect all of them precisely enough, we can go back and detect what actually happened in this collision. Now, most of the collisions that happen are completely boring. They don't contain anything that we don't know already. But something rare, for instance, like the Higgs boson, which was needed to complete the standard model, is produced in 1 out of 10 to the 13 of these collisions. So if you do your collider such that it produces 1 proton-proton collision per second, then you would get 1 Higgs boson in every 300,000 years. Now, obviously, we don't want to wait so long. So the LHC produces 10 to the 9 collisions per second. So what our detector needs to be able to do is to make a lot of very fast measurements. So for this, we obviously need a lot of electronics and data processing, and a huge amount of data processing. This shows a schematic view of the CMS detector. So the protons come in from the left and from the right, and they collide in the center of this detector. This thing is pretty big because to detect the particles of the highest energy, you need very large detectors that are massive enough to actually stop these particles. So you need a lot of material here at some point to really stop the particle and measure the full energy of these. And so the outer parts here, they try to really absorb particles, measure their energy. Some particles will still get through, and they are measured in these so-called muon chambers. These are the muons. While the innermost parts are the opposite. They're built as light as possible. They must ideally contain no material, and their goal is to simply measure the trajectories of the particles very precisely without disturbing their flight path. So we have these two different types of detectors. So the innermost, the so-called trackers, they track the particles without ideally disturbing them, and then the outer parts, the colorimeters, they try to measure the energy of particles by absorbing them completely, and then some particles still escape, and they are detected in these muon chambers. The whole thing is relatively big in the end. So this shows a photograph with some people for comparison. So this is the CMS detector during the construction. The whole thing is heavier than the Eiffel Tower, but it's just stuffed with electronics. So the whole detector has about 100 million sensor channels that try to find each and every particle that is produced in these collisions and record the data that is left behind in these detectors. So the innermost part, which is in this picture you see being inserted actually into the detector, is the tracker. This is a summary slide for this tracker. It has also several layers. Some have so-called barrel geometry, which you see here. So this is again the beam axis is here. Particles fly away from here and are measured in these silicon detectors that you see. And then the signals and the control are carried away by this mess of cables that you see here. So the whole detector contains 210 square meters of silicon in 9 million channels. This is the so-called strip tracker, and the innermost part here, very close to the beam, that's the so-called pixel detector, which is what we have worked on at PSI together with groups from the ETH and the university. It has about 1 square meter of silicon still, but a much higher number of channels, because it's not just dividing the silicon into strips as it's in this detector, but it's dividing them into little pixels, and so the number of channels, of course, goes up by quite a lot. And although everything is built to consume as little power as possible, because cooling is difficult in this region, because you need to you try to build your detector such that you need a very little mass that would obstruct the flight of the particles. So cooling is difficult if you want to do it without mass, but still, even though you build it to consume as little power as possible, these detectors consume several kilowatts of power. So as you can probably guess from the number of cables that are going out here, these detectors require a lot of electronics for different purposes. So there's the sensing element itself, which I'll discuss about in the next slides. But there's also electronics for data acquisition, for monitoring, and for calibration. And the whole thing needs to operate reliably for many years with almost no access. It's pretty difficult to get to these detectors once they are installed and the experiment is running. Okay, so how do you measure a charged particle in such a detector? In principle, that's very easy. You just need some material, and when a charged particle flies through, it will knock valence electrons out of this material, and this creates along the flight path pairs of electrons and holes. Now, if you apply an electric field to your material by putting electrons on the top of the bottom and applying a voltage, then these electrons and holes will drift in the electric field, and that creates short current spikes, which can in principle be detected. However, there's a bit of a dilemma here. In principle, you want to have a material here with a very small band gap. Maybe you remember the band diagram of insulators and semiconductors. So you have a conduction band, a valence band, which is usually completely filled, and a conduction band where you have no electrons, and then there's an energy gap. And to create an electron-hole pair, you need to deposit enough energy to bring an electron from the valence band up to the conduction band. So if you have a material with a large band gap, then the number of electron hole pairs is relatively small, because you need to transfer a lot of energy to produce them. So ideally, you want a material with a relatively small band gap in order to get a large number of electron hole pairs, which gives you then a nice and large current spike. However, the problem with that is that when you have a small band gap, you also have a large number of thermally generated charge carriers, which gives you a lot of leakage current when you apply a voltage here. So this material would ideally have to be an insulator. But insulators typically have to have high band gaps. So there's a bit of a trade-off. It's not impossible to do it with insulators, and our colleagues here at E2EH do this with diamond crystals. But there is an alternative, which actually most detectors or almost all detectors that are currently working use. Oops, there's one slide missing now. Ah, no, there is it. Because there's a trick that you can use for semiconductor materials, and that is of course the PN junction, which you know from the diode. So if you take silicon or any other band um, semiconductor material, and you have a p-doped volume at the top and an n-doped, sorry, a p-doped volume at the bottom here and an n-doped volume at the top, and you apply a reverse bias voltage, then you get a depleted volume here that you know from the diode, where there's very small current. So you can apply this volume, this voltage, and have no current. Still, you have the small band gap of only 1 electron volt. For diamond, it's more like 5 electron volts. So you get a lot more charge in the silicon than you would get with the diamond. Where a lot is still relatively small. So when you have a typical width of a silicon detector, 300 microns or so, then a charged particle that flies through creates about 20,000 electron hole pairs. So that corresponds to an electron charge of 0.3 femtocoulombs only. That's not too much. So if you look at the collection time, so the time to drift to the electrodes is about 3 nanoseconds typically. So you would see a short current spike of 0.1 microamp or 100 nanoamps for roughly 3 nanoseconds. So it's not a huge signal, but still much more than you would get with other types of detectors. No. Okay, so how do you measure such a signal? And you need to measure it fast because, as I told you, the collisions at the LHC happen at very fast intervals. Every 25 nanoseconds, we have several collisions taking place. So we also need to extract these signals very fast. And the simplest way to convert a current pulse into a voltage pulse is, of course, to simply connect a large resistor. So, for instance, if you have a 1 mega ohm resistor applied to your diode, so this diode here symbolizes the sensor, and you have a current spike here. Then, if you apply a mega ohm resistor, this current must flow through this resistor, and if the current goes down here, then this voltage, the voltage across the resistor will produce a voltage spike here, which is in this direction as well. And if you want a reasonable size pulse of, let's say, 100 millivolts, then you need a mega ohm. In principle, this would work. However, in practice, it doesn't. And the reason for that is that there's always parasitic capacitance. There's, for instance, the detector itself, which has typically capacitances of 10 femtofarad for a very small pixel detectors, up to many picofarads for a strip detector. And these capacitances will make it impossible to detect the signal. And on top of the detector capacitance, you also have the connection between the detector and your electronics, and the input capacitance of your electronics itself as well. Just to take some numbers, so if you have your 1 mega ohm resistor and you have a small pixel detector with 100 femtofarad capacitance, then you get an RC time for this combination of about 100 nanoseconds, which is much longer than the width of your signal. So you inject a current here, then this acts as an RC filter. And what happens then is, of course, that instead of seeing your nice pulse, you only see the first part of your pulse. And then before the RC filter reaches its asymptotic output value, the pulse has already disappeared again. So you only see the first step here, and then in that period, the current really doesn't flow to make your voltage drop across your resistor, but it flows from the capacitance through your diode. So all you see in the end is a small voltage step uh, that comes from storing the charge of your detector on the capacitor. So in this case, from the 0.3 femtocoulomb on a 100 femtofarad capacitance, you only would get something like 3 millivolts of signal. And that's not enough typically. So you need to do something else. And obviously you will need an amplifier, and in principle you can do something like this. This is an amplifier with negative feedback, similar to an operational amplifier, but one of the inputs, the non-inverting inputs, is simply fixed to a constant potential. Then this amplifier needs to have high open loop gain and negative feedback, in this case with a resistor, but it can also be a capacitor. So this amplifier, like an operational amplifier, then will do anything at the output to make sure that the difference between these two inputs is zero. That's the golden rule of the operational amplifier. It also applies to these amplifiers. And the effect is that this point here effectively is fixed. It becomes what is sometimes called a virtual ground. So here you have a point that is always at ground potential, but you can absorb the current here and measure it because it has to flow through this resistor, which is the first golden rule of operational amplifiers. So the nice thing here now is that if this amplifier is really ideal, so it is infinitely fast and has infinite gain, then the fact that this is now like a ground node means that the effect of the capacitances disappears completely. Obviously, this is only true in case that your amplifier is ideal, which it never is. So capacitances do remain a major concern here, but you can reduce the impact of these capacitances a lot by using a capacitor, an amplifier here. So this has been done for many years, and I'm just showing this old picture of one of the first silicon detectors. So here's like a 10 centimeter large silicon detector, and the amplifiers are here now discrete amplifiers, which are arranged here on a huge area around the detector. Discrete amplifiers, because you need a separate amplifier for each channel of this strip detector. So this is it worked. It was in a so-called fixed target geometry where it was enough to measure particles flying through this little volume. But obviously that doesn't work in a detector like CMS, where everything needs to be compact. So this picture clearly shows why we don't use discrete amplifiers, but we need to go to integrated electronics for our detectors. And then that looks a bit like this. For a pixel detector, for instance, you have this the sensor here, so the diode with the N implant and the P implant, and then you attach directly to that a readout chip using a so-called bump bonding. So there's a small indium ball sitting on the top of the detector that connects the sensor with the electronic, and here you have your amplifier with negative feedback. In this case, it doesn't have a resistor, but it has a capacitor in the feedback, so it doesn't produce a voltage spike, but it integrates the current that comes that is produced by the particle that flies through this detector. And by integrating this, you measure the total amount of charge that is deposited, and that can be useful in order to interpolate between adjacent channels. So when a particle flies through these detectors, it usually deposits charge in not one, but two or more pixels. And then if you measure how much charge it deposited in each one of them, one can interpolate and increase the position resolution of the detector. So this shows a wafer with 3 of these silicon sensors for our CMS pixel detector, which was designed at PSI. So these are each one of these is 1.6 times 6 centimeters on a so-called 4-inch wafer here. So each sensor has 66,000 individual diodes. Each one of them has a dimension of 150 micrometer times 100 micrometers. And each one of these 60,000 diodes needs to be connected individually to amplifiers on a separate ASIC. This ASIC is shown here. So 16 of these are mounted to each of the sensors that you've seen. It has 80 by 52 pixels. So in total, this is 1.2 million transistors. What you see on this picture here are these indium bumps. They have been deposited on the electronics. What you still see is the surface of the electronics is not flat completely. If you look at it very closely with a microscope, you see a bit of the structure of the metal lines that carry the signals around. So here you see a close-up of 1 pixel. This is the like only just a metal pad that is where the indium bump is connected, and this is the amplifier. It's a very simple amplifier. It's far from being as complicated as an operational amplifier. This one, in fact, consists of only 2 times 2 transistors. But it needed to be simple, and because you need so many of these, and the rest of the pixel is then filled with digital electronics. So each pixel has about 250 transistors. So you have, like I said, the amplifier. You also need a comparator which decides that there has been a hit or not. One needs threshold corrections for these comparators because in microelectronics you always have to fight variations from transistor to transistor, and if it's not possible to make everything big such that these variations become small by averaging out, then you have to be able to correct every single transistor, every single amplifier by applying threshold corrections. So these are done in a digital way. You also need logic for reading out the data and for injecting calibration signals. So this whole thing consumes about 33 microwatts of power, which sounds like not very much, but then the whole detector in the end still consumes several kilowatts of power. For the full detector, we had to make 16,000 of these chips. So if you go to a commercial vendor and ask them to develop a chip for you, for which you need 16,000 of, they will typically laugh at you because in industry chips are usually produced millions of times. So these we had to obviously design ourselves with very specific requirements for our experiment. Had to be radiation hard and all that. And so designing this ASIC for us was about 50% of the R&D time of the detector. But there is, of course, a lot more. And that you can see here. So this is 1/2 of the detector. I think I've shown this picture before. You see a large number of these modules here. And in the end, to the outside, there's always this mess of cables that bring out the data that is read out and have to bring in the power and all the control signals. And here's a desk in our laboratory where we test some of these modules. Here you see a stack of modules where such tests are made, and this is a sector of a detector where auxiliary electronic which is used to operate and control the detector is being tested. So this is the kind of setup that we use where we replicate parts of the final detector and test them before the full detector is finally built and installed. So this is the present pixel detector, which has already operated at CERN for several years. It was at PSI recently for refurbishment and some repairs and has been returned to CERN now a couple of weeks ago and will be reinstalled in next summer to operate for several more years. In parallel, we're now operating on the successor of this detector, which will hopefully go into operation in 2026. This time we're not working on the barrel part, but on the end cap. So here the detector has a different geometry. So here we need to now fill a disk area with individual modules that this time look like this. And for this detector, we're now trying to get rid of the mess of cables that we've seen. So we're trying to put all the connections into this very special PCB. So it needs to be lightweight. So we removed every bit of material that is not needed, is cut away. And then all the signals and all the power lines have to go through the pieces of material that are left over here. And eventually all these positions will be populated with modules. And the PCB has to carry the so-called serial powering. This is a new concept. So the power to the modules is not brought in module by module, but the current for each module flows in to the first one and then out again and then into the next one and so on. So all these are connected on a chain, pretty much like the lights on a Christmas tree, which is, however, quite a complication for precise electronics, because you need to make sure that something that this module does not affect what happens on the other modules. So this all needs to be tested, and that's work ongoing at PSI in conjunction again with the University of Zurich, where this PCB has been designed, and also at ETH. There's also a group, a CMS group at ETH here. So, and the key question here is always how much can you reduce the material of your detector without compromising the electrical functionality. Another thing we're working on is for the next generation of detectors, where we hope that we can not only measure the precise position of the intercept of a particle with the detector, but also the time when it passed through with high precision. And for this, we're developing components here. In this case, it's a time-to-digital converter. So there's not only, as you've learned in the lecture, an analog-to-digital converter, but there are also time-to-digital converters, or TDCs, which are in principle precise clocks. So you get a start and a stop signal, and you count. You need to count how often an oscillator oscillated in the time between. So. And such a TDC also needs to be integrated into an ASIC of a future readout chip. But before we make a large readout chip, as you've seen before, where the production is relatively expensive, we usually produce small samples that can be tested, that can be produced relatively cheaply. And then we get these test structures. You can see it here, which is just a few millimeters large. But to test these test structures, you have to then design your own custom electronics that can, again, test this. So this is shown here. There's a little board that has the test structure itself, which is really tiny. And this board carries, for instance, 2 precision delay chips, which create the test signals. And then you can see the traces here, which have to be designed very carefully as transmission lines to make sure that the control signals, the start and the stop, arrive at your test structure undisturbed with exactly the shape that they are supposed to have, and without any reflections that would disturb the precision timing. We're talking about picoseconds here. So that really needs to be designed very carefully. And this was, of course, designed in-house here. And then more and more we combine these things now with Raspberries, which are extremely convenient. This is a Raspberry, which is very helpful because it can directly talk to these chips and ADCs and TDCs, and is read out via a network, which makes things very easy for us compared to all the setups. So this is just the kind of thing, smaller projects that we have several of ongoing at PSI. So the largest thing that we're working on is the development of monolithic pixel detectors. So these try to use the fact that already inside a normal CMOS chip, you have a depleted region, and these depleted regions also act as detectors. So this is used in some some chips, for instance, in CMOS cameras that you have in smartphones, but also in some recent cameras. But it's also sometimes an unwanted process and can cause what is called a soft error in electronics. So sometimes even processors do things they're not supposed to do just accidentally, randomly, and sometimes that's due to a cosmic particle flying through this. So we, of course, want to use this systematically. So the depleted region around the source and drain in a normal CMOS is too small to reliably detect particles, but there are now developments for creating larger depleted volumes. And this is a very active field of research, which we also started working on. And this last picture shows one of the researchers, which some of you probably know, working on the development of such a detector. Okay, so this is all. I hope you learned something in this lecture that will be useful for your future life, and we wish you happy holidays and all the best. If you have questions, let us know. Okay, thanks everybody.